All right, hello, give me a minute, I'll get that up here. Okay. Good Lord. Okay. Okay, how many more weeks of school here? We have this week, then 1, 2, 3 more. We only have lecture for 1 more week. After that, everything will be office hours. And let's see, Wednesday we have the reading/study day. So there's no classes on Wednesday. We normally have office hours then. I'm undecided if I'll hold them, but you know, I've been sitting in on your team meetings, and if you need me, just get a hold of me. I have office hours now from 9 to 11 too. I'm going to hold those for sure on Wednesday. I think we have a Sprint 3 stuff is due today. I don't care if it's a day or two late. That's not a problem. I think I'm in enough of a rhythm now with those that I can get those turned back around though quicker. Probably the best way to send them to me, the assignment I think says group discussion. That's one way. If you send me a message in Canvas with everything zipped up, I'll be sure to see it right off the bat, and I can save it and score it. Let's see. Let's do the slides, then we'll have some discussion, then we'll open it up to discussion about just more general topics. Hold on here. Let's see. Okay. So we've been dealing with Agile Scrum this semester. That's the process that we've been working with. Hopefully you're starting to feel comfortable with it, or maybe you already are comfortable with it, but there's a lot of other processes out there. People have been building software now commercially, say since the mid-50s. So we're looking at some, 65 years of development, awfully young in terms of engineering disciplines. But people have come up with different processes. Computer science is a pretty new field. You could argue maybe 80 years old. Software engineering is a much newer field. I'd say, I would argue it's 40 years or less, where people really started to look at, hey, we keep making software and it's all crap. Maybe we should have better processes here, and starting to really study the process of making software. In the meantime, industry and research groups had already been making software, so they developed processes on their own, and then other people came along and cataloged them. Some of these you already know, some of these you may not know. When I was in industry, I had direct experience in most of these. I'd say everything but the V-shaped model, not necessarily with software, but these things also can apply to hardware systems too. Okay, software development lifecycle model, a framework that describes the activities at each stage of software project development. Think about how this works for Agile. Agile has a framework for what you do, right? You have the kickoff meetings and the initial determination of the product. Then you have sprints, and each sprint is well defined with the sprint planning meeting, and then the sprint itself, and then the sprint review, sprint retrospective, product demonstration, right? These are descriptions of what happens in each phase of the project. And in the Agile Scrum method, once you get into your sprints, each phase is identical, not in terms of content, obviously, but in terms of activities. That's not true for all the models. Most of the models have some kind of a progression from one phase of design to another, more akin to traditional engineering. So since each of these are a framework, that doesn't mean that they really describe necessarily the process. All of you in your teams have taken that Agile Scrum framework and modified that framework to some degree to get a specific process for your team. And hopefully your team is not as chaotic as it was the first sprint. You've settled into some kind of a routine. And if I were to ask you, what is your process? You could say, oh, we're using the Agile Scrum framework and we largely adhere to that. But our specific process is we meet Tuesdays and Thursdays and Saturdays. We do blah, blah, blah. So the framework describes the skeleton, and then the individual groups that are doing the work will have their own process. So when you get a job and you work for Lockheed, that they're going to have a different process than if you work for Boeing. Then they're going to have a way different process than if you work for, say, Google, or if you work for a startup with 3 people in it. But you can take the process and say, oh, we belong to this framework. So be aware of that distinction. We're going to talk about the frameworks, but then every entity develops the specifics of how that framework gets implemented in their situation. And everybody's trying to do the same thing. Produce not just software, but verified and validated software. Now remember what validated means. In terms of commercial software, validated means, are we building the right thing? In other words, are we satisfying the customer's needs? Is this really what the customer wanted us to do? And verified means, okay, once we convinced ourselves that we know what the customer wants, we can prove to ourselves to some degree that we actually did it right. And of course, that's normally, we think of testing, but we talked about all kinds of software verification and validation along the way. Meetings with the customer, design reviews, walkthroughs, team reviews of code, of different artifacts, code, software design, test plans, and then the actual test itself. Because everybody's trying to solve the same problems, what you're going to see is a lot of overlapping between these techniques. If everybody has to do the same job and they're coming up with different frameworks to do that job, because they have to touch the same bases as they go around to get back to home base, they're coming up with variations on a theme sometimes. You're going to see a lot of overlapping ideas. So when we talk about agile methods, which really came about in the 90s, it's pretty new. And people talk about it like it's this new way of doing things. Yes and no. It's a new way of doing things, but you can see its roots in the way they built software in the 70s and in the 80s. So you can, if you know what to look for, you can see that it's building towards agile. And of course, agile is building towards something else that we don't know what it is yet. You guys will probably invent that. But if you look, object-oriented software, You build classes, you have data encapsulation. Oh, in the 70s, they had something called structured programming, where you take the large task and you break it up into components. And each component had its own authority, supposedly its own authority over its own data and over its own tasks. And then you integrated those components together. Software understanding, we try to do things in code so that you have in-code documentation or code design techniques that are supposed to be intuitively helpful in understanding software. Oh, in the 80s, there was a whole programming language developed called Ada. And of course, Ada, its goal was to standardize software, written software, and to standardize how things were done. So you get to see these roots if you go back in time and see how things came about today. Why? Because people are trying to solve the same problems in the 70s and the 80s that they're trying to solve now. Building this software. Verified, validated, oh yeah, everything changes on you all the time. Software is not physical and therefore seems to be, and this may be bias on my part, seems to be more hard to nail down in an unchangeable way than hardware products are. And again, I've worked in industry on hardware and software products, and the hardware products seemed a lot more hard to change. Once people kind of accepted that, you know, once you had the metal bent and things put together, that's kind of how it had to stay. Comments so far? Okay, after we go through these models, I want to come back to this idea and let's talk about, you know, what are your experiences? What are you learning? What are you seeing in terms of, you know, you guys have some degree of experience now, right? How does this all play out in terms of what's trying to be done here? Okay, waterfall model. I think this is the most common model still. I think this is the model that came from engineering of the physical devices. That's what I think. I'm not 100% sure. And when I say I think it's the most common, I haven't done any studies. I should say it's the most common across engineering. Right now, the most common, the most popular, let's make a difference. The most popular in terms of how people feel about it right now are the agile methods. However, there may be so many heritage pieces of software out there in large industries that are having a difficult time adapting to the agile roles that are still doing waterfall. This may still be the one that has the most dollars spent on it, or maybe the most numerous in terms of software development, possibly. This is the one that I think in EGR 101 you get it introduced to. If you are in mechanical engineering, aero engineering, this is probably the one you're going to get introduced to. And it's step by step. You know, it makes sense, right? That's one of its advantages. It makes sense, step by step. Oh, you make the requirements, all the requirements. Then you make the design. Then you implement the design. Then you test the design. Then you install this thing, and then you maintain it. So that's the whole life cycle. Now, again, in a physical world, this makes perfect sense. So we would, in a physical world, you might need to do, well, I'll give you some examples. So we used to do these avionics boxes, and the avionics boxes were bolted to some structure, and then they would go up in space, and it was probably a good idea. These were days of shuttle launches in area and some Delta launches. Probably a good idea when the thing launches that the boxes don't fall off, right? That's a good idea. And so what do you have? You have requirements. You have requirements stated to you in terms of environment, in terms of margins of safety that you're allowed, in terms of you know, the weight and CGs of the boxes. And you can take all of these different requirements and come up with models and make predictions about, okay, here's how we have to design it so it doesn't fall off. Then you implement it. That means you go build the box, and then you test it. You put it on a giant vibrator called a shaker table, and you shake the hell out of it and see if it falls off. And then you install it in the actual flight hardware, and then maintenance doesn't mean too much for satellites. Once they're up there, they're up there. But for software, same thing. Work through all the requirements, come through the design, code it up, test it, install, meaning deploy the software and its usage. You know, think of a restaurant. People open up a new restaurant. What do? They've got to go deploy software to that restaurant. All of the ordering software. There's even, you know, there's sophisticated software about how you cook the food, how the kitchen prepares the food. And all of the customer credit software, all of that stuff, inventory software that gets deployed or installed at the restaurant, and then maintenance. Now for software, maintenance is a good thing. I mean, that's where people can make a lot of money. You install software at a restaurant, and then you know, that software needs to be maintained, maybe upgraded periodically. And how long is it going to be? How long is that restaurant going to exist? You know, 30 years, 40 years, 50 years. Oh, okay. So maybe you can keep that initial contract for the software going for a long time. And believe me, 30 years of maintenance is probably going to be a better profit margin than 1 year of development. So that's how that works out. Now, maintenance on physical things widely depends on the physical thing. How many of you guys have worked with this model in your academic world in the past, in some project, either EGR 101 or somewhere? Right. And what was the project? So 2 people are saying yes. What was, remember what the product was? It's like 2 years ago, right? 3 years ago. Programming a robot to follow a line. Okay, with Leo, probably. All right, so programming a robot to follow a line. So you have requirements, and you followed this model because you have all the requirements up front. You know, he's designed it that way. Design it, implement. Now, that was an iterative process, I'm sure. And then you test it and install. And now the maintenance. Oh, man, how much maintenance did you do? Like none, because in an academic environment, we can't force you to be here for 20 years. This feels like it, but we can't actually do that so that you get to experience the maintenance aspects. Sarah, what was yours?
Sorry, I stood up to go get water. So mine was EGR 101 as well, but
Okay.
not the software one. We were trying to like make this random doohickey. Every team had a different doohickey
Right.
that they were working on to try and
Okay.
solve some problem on campus. So
okay,
yeah,
go ahead.
we defined the problem, which was that when it rains a lot here, when you open your car door, the inside of your car gets wet. And then we like designed a little retractable device that would like keep your car from getting wet, and then
Right.
prototyped it, and then the semester ended. So we got kind of like halfway through
Yeah.
The waterfall model. And
that's the problem with the, you know, the artificial environment that we're in with academia. Not much, it's hard to get around that. Faculty is always working hard to figure out how to give you a better simulation of the real world. Okay, so there we are on the same thing, requirements and analysis, design, construction, testing. Now, without moving on to the next slide, you can guess what the problems with this are. You may be able to guess what the benefits of this are. You know, the waterfall model is kind of taking a hit because everybody loves Agile these days, but there are advantages to the waterfall model. The biggest drawbacks, you can probably guess. What would you guess is the biggest drawback to the waterfall model for software? It's that requirements block. You got to get it right, and you got to get it right up front before you do any real development. And you guys are already experiencing this, I hope, in your teams as you develop the product. You're finding out more about the product and refining what you thought your initial product description or requirements were. Right. So Christopher says they make one mistake towards the end and it takes forever to restart. I'm going to reframe that. I'm going to say that you find the mistake towards the end. The mistake was probably made in one of the first two blocks, requirements analysis or software design, and you don't find it till the end. And now you have to go back, and there's all that cost of redoing the portions of the requirements analysis and the software design. To make that worse, if you're in a industry whose process, remember this is a framework, but if you have someone whose process has a very heavy documentation tail, then that gets even worse, because the process by which you modify things is very costly and bulky, because the whole momentum of the documentation, just like things have a physical momentum, the momentum of the documentation is hard to change course. But what are the strengths? Oh, it's so easy to understand. There's a reason why you saw this in EGR 101. Your introductory engineering class. It's easier to understand. It provides a lot of structure to people who aren't used to doing this. Everybody gets the milestones. That's both good and bad, by the way. It's good because you give the illusion of progress to your customer and to yourself. The bad thing is sometimes you actually are making progress, but you haven't hit the milestone, and then the customer gets all freaked out. You have requirement stability. That is a strength. As you know, though, if the requirements were wrong to begin with, then that's not necessarily good. But why would requirement stability be a positive thing here? Well, because remember what I said earlier, software seems to be more unique than physical devices, where people always want to change the requirements. Even though you're halfway done or 50% done or almost ready to deliver, people are like, well, we could just make the software do, you hear people say that, oh, it's just a software change. How easy is that? It's just a software change. So having those requirements set in relative stone, maybe set in mud, is a positive thing, because it resists what we call scope creep, right? It resists people arbitrarily or changing requirements for you. Good for management, and it works well when quality is important. Now, think of that. Quality is important. Where again do we think of high quality items, software? High quality systems?
Stuff that people's lives depend on, like airplanes.
Right. Safety critical applications are the primary thing. So we're talking about Embry-Riddle's domain, aviation. You screw up, people die. That's a serious thing. So you've got in this tight stuff, real-time software for autopilots, for sensors, spacecraft. All right. So by the way, the levels of risk, at least as far as NASA is concerned, is loss of life or major damage, like loss of a limb or something like that to a human. That's the worst thing. And then the next one is loss of vehicle. And then the next one is loss of mission. And then the next one is degradation of mission. The first two are really the ones where they normally focus on where you have to have quality, you have to have redundancy, right? You're not allowed any single point failures, that kind of thing. Once you get down to loss of mission, depending on the mission, right? A mission to Mars, a loss of mission and a loss of vehicle is the same thing pretty much. So that's also tough, but degradation of mission is generally where they start to back off the quality restraints. But that's where you're going to be really focusing on things. Medical devices, that's where quality is important. But wherever you have either human life or really expensive vehicles, you know, these F-35s that are in the news now, because they apparently, I haven't read the articles, but I guess I'm hearing they're, you know, super expensive. What a surprise, but not that good, you know, you know. Well, you don't want to lose one of those because of a software issue. Deficiencies. You got to get it right. Requirements must be known. You got to get it right. And it inhibits flexibility. What do we know about flexibility in terms of software creation? Change will happen. Change will happen. The way I view it is everybody's trying to manage change. And Waterfall does it by trying to constrict change. And Agile is trying to do it by preparing for change. Gives a false impression of progress because, again, hey, I hit all these milestones. Well, that's great. But if at the end it doesn't pass test, or at the end, when you deploy it, it doesn't work the way you thought it was going to, because deployed systems are behaving differently than simulated systems. That's not progress. Integration is one big bang at the end. Yeah, that's a problem. That's a problem. And it's pretty opaque to the customer. They say, here's all our requirements. And then they go away. And a long time later, you say, here's your product. And then they look at it and it's like, well, this isn't at all what we wanted. So that's a tough thing. They're, if you, again, look at the agile model, ideally that you're in constant, semi-constant touch with the customer. In a perfect world, you have a customer as part of your team. A customer representative is part of your team. They're buying into all the decisions at the daily level. They are not controlling the team. They're not the boss of the team, but they're aware of what the team is doing. And that's all good stuff, as opposed to an opaque system like Waterfall. When requirements are known, product is stable, technology is understood, meaning safe. You're not saying, hey, let's invent a whole new thing. New version of an existing product. Now, look at that. What does that mean? A new version of an existing product. What are the characteristics of that? Well, the requirements are well known, the product is stable, and the technology is understood. Porting an existing product to a new platform. What are the characteristics of that? Well, the requirements are well known, the product definition is stable, and the technology is understood. Notice it didn't say safety critical. Well, that's because Waterfall is a good choice for safety critical. It's not the only choice for safety critical. By the way, again, more and more people are trying to adapt to the agiles. They're the current hot fad thing. They seem to be very good. All the traditional companies that were using Waterfall are trying to adapt agile to their teams. So people are learning or experimenting with the idea of taking, say, Agile Scrum. Now, Agile Scrum, think back. What do you know about Agile Scrum? What's a size teams does Agile Scrum work for? What's probably an upper bound for a team size for Agile Scrum? Around 8, yeah. I think some people will stretch it to 10, and I think really optimistic people stretch it to 12. But I'm pretty pessimistic about that. Yeah. Now, what if you have a team of 300? What do you do? Can you use Agile? So people are trying to learn to adapt Agile to that. So they're converting from a waterfall model to Agile. So even these traditional industries, like I said, they are moving to some form of an Agile method, and they do that by basically abstraction or aggregation. You have a team of 8, then you have 8 teams that come together, and their managers or their product owners form a team of 8, and you can keep doing that. So you have scrum of scrums and then scrums of scrums. Okay, the V-shaped model. This is the one I don't recall ever having direct experience with this, but what you're doing is you're taking the waterfall model basically and making it a little more finely granular. So if you notice, instead of 1 requirements phase, there's 2 requirements phases up in the upper left-hand corner. And then instead of one design phase, there's two down in the, on the left-hand side. And then you have, instead of quote testing, you have unit testing and integration testing. That's actually true in the waterfall model. It's just that most people don't break out those things. And then, I'm sorry, so there's actually three of those. And then you have the actual product operation and maintenance. And what you're doing is you're planning those out at the same time. That's why those arrows are going across. You're not doing them at the same time. Obviously, you couldn't do requirements planning and product operation at the same time. You don't have the product yet, but you're planning them out at the same time. Now, why does that make sense? Well, if you think about how the product is supposed to operate, that helps you drive your requirements. And then this requirement specification and analysis and system and acceptance testing, same trick. If you think about, instead of asking the question of how do we specify the requirements, what you're really doing is asking the question, how are we going to test this thing? See, the way we do it, the way I presented it in class, it's like, write your product specification and then ask yourself, how are you going to test it? And I always encourage you to think of those two things at the same time, but I'm framing it from a requirements drives the test point of view. And instead they're thinking, well, how are we going to test it? Now that will help us define the specifications. Integration and testing helps you define the high-level design, and the high-level design helps you define the integration and testing. So these are natural pairings of things. And then the coding. By the way, if you notice, the coding in these things is always the smallest, boring, simplest part. If you're doing the other work right, the coding is relatively mundane. And it's awfully hard to convince people of that. So here's more of the same chart again. And I already went through this. I don't think I'm gonna go through this chart, but let's talk about strengths and weaknesses. What's the strength? A lot of verification and validation. Look at that, all of these quality review steps. See, a lot of verification and validation. And in the early stages of the product, because you're reviewing, how do these requirements bounce against the testing? How does the testing bounce against the requirement? You're getting that all throughout. Verification and validation all throughout. Each deliverable must be tested. And then you can track progress by milestones. Easier to use. So you still have the milestones here. What are the deliverables? Oh, let's see. What are the deliverables going to be? Think about this. Early on, you're going to come up with a design and a test plan at the same time. You're going to come up with detailed design and unit testing at the same time. So you don't ever finish a design unless you have the companion, here's how we're going to verify this design is good at the same time. Now you may notice, again, everybody's doing the same thing, so there's going to be some overlap. I'm encouraging you, when you do your sprints, in the sprint planning meeting, you pick a task and you make a requirement for those tasks and you make a test case for those tasks, all in the same meeting so that your team can review and approve those things. Fair amount of work. Your design at the detailed level, again, your high level design is the structure of how your objects all relate to each other. Your design at the detail level would be the actual, I would say, what's happening for a given method or a given series of methods. Okay, now how do I test this method? So notice there's a bit of an overlap between what I'm asking you to do in the sprints in this V model, because there's some concurrency in terms of thinking about, okay, I have this task, how am I going to solve it? And thinking about, I have this task that will result in a piece of software, how am I going to test it? That's unit test, right? The low-level testing. Does not handle concurrent event. Oh, I'm not sure what Ochoa meant by that. I have to look at that. It does not handle iterations or phases. And again, just like the waterfall model, it's one time through. Doesn't handle dynamic changes and requirements. Again, why is that? Because it's one time through. Doesn't contain risk analysis. I'm unclear about concurrent events. Now, what does this mean? Doesn't contain risk analysis. Typically, when people use the waterfall model, you'll hear management talk about risk analysis. So what happens if we're this far along and something goes south? What happens if we're this far along and something goes south? What if we, what should we do before we move forward? And then sometimes you'll do some prototype testing before you move forward. Why? It's risk mitigation. Rather than putting it all together and hoping it works, you actually may build little components of your software and test it. You're thinking, oh, okay, this all works great as long as we have the system bandwidth is, some big number. Oh, okay, maybe we shouldn't wait to find out. Maybe we can build a small, simple simulation of our completed system handling requests like a queuing model and determine if it can handle that bandwidth. So you've got some prototyping that may go on early on. That would be a form of risk mitigation. You can do that here, but you're working with the two products at the same time. It would be you can still do it. I'm sure you can still do it, but I think it's not built the same way. Hold on, I'm going to go hang up on these people. Maybe if I can figure out how to mute myself. Okay. Sorry about that. All right. Okay. I've not worked with the V-shaped model. Prototyping model. This is a fairly, even in the mechanical world, this is a fairly well-used model. And what's the idea? Build a prototype. And then you check it out. They give feedback, refine the prototype. So this is an iterative model. Notice the concept of iteration is going to show up a lot. Once you get past waterfall and V model, this concept of iteration shows up a lot. Why is that happening? You're responding to change and you're doing risk mitigation. Risk in terms of validation of the validation and verification of the product. I often encourage students in CS225, they're like, oh, I'm having trouble with my project with the GUI. And I always say, well, what you should do is put your project away and build from scratch a really simple GUI. And then you'll learn how to build a GUI, then go back and continue your project. And I don't know that anyone's ever done that. But that's always my advice to them. Well, what am I really doing? I'm telling them to build a prototype and see if it works. Oh, I want to figure out how to swap screens. I want to figure out how to make this thing change into that thing. Okay, forget your project. Work in this little tiny space where that's the only problem you're trying to deal with, build a prototype. And they're learning the skill in that case. Here, you're developing a prototype for some kind of evaluation. And as you know, prototyping is a fairly universal engineering practice. Well, maybe you don't know that. Now you know that. It's a fairly universal engineering practice. Build something, check it out, see if it really works. Notice it's basically waterfall iterated. Until you get to the operations and maintenance section. So again, if you look at, can I do this? These boxes, that's waterfall, isn't it? Right there, that's waterfall. What are you doing early on? You're prototyping. And again, what are they trying to do? Why are they doing that? They're solving that same problem. We don't want to find out we got it wrong way down the road. So the prototype gives us less risk that we've done the wrong thing. It's a valid, would you say it's a validation step or a verification step? Or is it different depending on which box you're looking at? No takers? What's the difference? What's verification? What's validation? Yeah, right. So validation is building the right thing. And notice, by the way, what they're saying here, system testing, right on the screen, validation, validating system requirements. So this first thing where you're doing requirements analysis to prototype, meaning you do build a prototype and you give it maybe to your customer. Hey, this is a real simple mock-up, but we wanted to know if this is what you wanted us to build. That's validation. And then verification is that you actually built the right thing. So when you're doing the testing, you're verifying that your design is correct. But even here with this design to prototyping, I would argue that you may have an aspect of validation there because you're going to the end user or you're going to the customer and saying, hey, does this design work for you? So really, what are you doing? Verification is just, did we build what we intended to? And then validation is, did we build what the end user wants? Did we build what the customer wants? And remember, the customer and the end user aren't always the same people. So I'd say this prototyping is primarily a validation exercise, especially early on with the requirements analysis. Okay. Preliminary plan, high-level paper model, requirements specification, right? You're doing all the steps, but you're doing it in a sandbox, if you will, right? You're not building the actual product. You're building a simulated version of the product, maybe even just a pen and paper version of the product. And that may literally be, instead of a real active GUI working on a machine, here's a picture of what it's going to look like. Here's the buttons. You've seen people in movie design and in game design, they do storyboarding, and it's literally drawing pictures on the wall or drawing pictures on, sheets of paper one after the other. It can be that, basic, or it could be a partially functioning simplified system. Okay, then you keep doing this till the user is happy. Once the user's happy, you're actually, a couple things can happen. You might rebuild to the recreate that sandbox in the production code, because maybe you have different rules of how you were, different software practices, coding practices, or if you quote done it right, then the prototype eventually evolves into the actual product. What's the strength? Oh, customer can see it happening. Remember, the waterfall could be opaque to the customer. Here, the customer is actively involved and they're seeing what's happening. So you get a better sense of validation. Developers can learn from customers. And I'm going to say that works two ways. The customers can learn from the developers. So remember, one of the initial problems that we talked about with software engineering, and this is, I would say, true of any engineering, but maybe particularly software engineering, is that the customers don't know the software world. They don't know what is and is not capable necessarily. They may not have a real experience, especially if they're trying to develop something that's really new to them, or have developed something really new to them. If they're saying, look, we bought this tool and we don't like it, so we want you to make another tool for us. Well, they've got experience with how the old tool worked, and so they would have a better expectation of how your new tool will work. But if it's something brand new, you know, people don't often understand what computers can and cannot do. There's a mythology about computers, and so you have to, they don't necessarily know what's possible or what's impossible. In addition, they don't know the language. Just why should they? It's not their job. So it's difficult for the customer to talk to the developer. On the other hand, the developers don't know anything about their business. Why should they? So the developers get to learn from the customers about how this thing will actually be used in day-to-day operations. You know, it's a good idea if you can do it. If you have a customer and you're a software developer, you know, go to the customer's place and watch them, watch what they do, watch how they use their existing software, or watch what problems they have because the software they want you to develop doesn't exist yet. So this is a two-way street. You, the software developer, gets to learn from the customer how they're going to use the product. On the other hand, the customer can learn from you what's possible. The customer may say, oh, I want to do blah, 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 blah. And you can say, you know, it's a lot easier if you just do this, and then you get access to all those things that you wanted. I mean, we can meet your functional requirements, but we're going to meet them in a way that you didn't envision because you didn't know it was possible. Oh, that makes a happy customer. More accurate end product. Well, we hope. The unexpected requirements are accommodated. Gosh, it sounds like Agile, doesn't it? Flexible design, visible signs of progress. Each prototype is a little more sophisticated. Interaction with the prototype stimulates awareness of additional needed functionality. Ah, that's great. Again, when in the Agile process does the same thing, right? You do a product demonstration, and ideally that product demonstration, you actually deliver a product to your customer, and they have someone who's working with it and playing with it and saying, yeah, I like this, I don't like this. You know, there's very much a prototyping aspect to Agile methods. What's different here? Oh, the process in Agile, like especially Agile Scrum, has specific milestones of the sprints and the Scrum meetings, right? That kind of thing. Whereas this is more waterfall iterated. Uh-oh, tendency abandoned structured program development. Bad reputation. Why? Because people didn't follow the process. Customer may want the prototype delivered, and process may continue to forever. Okay, scope creep, right? Everybody says, oh, it's just software. Of course we can have it do this. By the way, those first two, Agile has that problem too. Again, there's a lot of overlap with these things. It used to be, I would say 10 years ago, people would say, oh, we're Agile, And what that meant is they had no process whatsoever. And about 5 years ago, people started to hush those people up. And now, hopefully, people have a better thing of Agile. Those first two are relatable. Relatable, you mean you've experienced those, or they go together? They do go together. Yeah, yeah. So even when you're Agile, you know, there's a reason why I'm pushing you on structure, on process in the Agile, and I'm not worrying about your code all that much. I'm looking at process. Why? Because what's the first thing in this class? Easily half the teams, you know, CS225, I give a really watered down version of process to them. I'd say 80 to 90% of them completely ignore process, or I should say, don't appreciate that there's value in the process. And so right off the bat, it's like, okay, boom, we're going to go code. Oh no, that was not the process. That's not the process. So be aware of that. Process actually is important. What if the process is hindering you? What should you do? Change the process, but don't abandon all processes. Adapt your process. What if you work in an industry, in a company, and they already have their process, but the process is a pain in the butt? Work with them to try to change their process. You know, there's levels of maturity in organizations. And the first one is no process, and the next one is we have process, but it's all like oral tradition. And then the next one is it's written, but you know, people don't really follow it. But the highest level is you actually have processes by which you develop your processes. So if you don't like the process, adapt it if you're able to. And if you're not, then work with the people who are in control of the process to modify it. All right, when are we going to use this? Requirements are unstable. Oh yeah, this is good, right? It's like, oh, we think we need to build something, but we're not really sure what it is. Okay, how about this? You know, here's a prototype. Is this what you had in mind? And what that interaction is going to do is make them think, yeah, but we were going to also use it this way, but we don't need this part. You get the interaction, which gets people to think through what they really want, because they're simulating actually using it in their workspace, not just as a brain exercise, but as a, how would you handle this with a real piece of software/hardware that they can work with. Develop the user interfaces. Why is that? Because it's the users giving you feedback, people acting as end users. Short-lived demonstrations are good. Yeah, so this short-lived demonstrations, where would that show up? That's a weird thing. Well, sometimes people aren't sure if they want to buy something. Sometimes people aren't sure if they need a product. Sometimes people aren't sure, or sometimes your company might want to go bid on, you want to become the contracted to a contractor, some big money contractor, and you're wondering if you should even put in a bid. You know, man, if we get this medical system, we're going to be in 1,000 hospitals across America. We're going to make $1 billion. It's great, but it's a really big effort in terms of resource. We're not sure if we have the expertise or the capacity or the whatever. And we're not sure of our idea. Oh, okay. Let's take 2 months, build some kind of a simulation and a prototype to convince ourselves that we should even bid on that giant contract, or better yet, to get better information as to how to frame the proposal. Or better yet, to invite the hospital bigwigs in to say, hey, look, here's our demo. Here's what we think you need. Incremental. Incremental and iterative are kind of similar, but there's one difference. With incremental, you build one little piece of the overall product. And then in the next increment, you add to that piece. And in the next, you add to that piece. And in the next, you add to that piece. And in the iterative forms, you build the whole thing, but at a low granularity. So for example, the incremental form of object-oriented is you build, you have to build 20 objects, 20, you have to define 20 classes, and you build, 2 of them. And then you go through another cycle and you build 2 or 3 more, and you go through another cycle, and you keep going through these cycles till you have them all built up. Or you build, if you break your thing, think of your software system as a system, and you break it into 3 or 4 chunks, and you build this chunk, this chunk, this chunk, and you're adding functionality. That would be incremental. And then the iterative forms are, you build the whole thing, but it's really high level. And I like this form sometimes. Not that I get to code very much, but you build out all the classes. So you have to build 20 classes, you build out 20 classes, but none of the methods work, right? All the methods return dummy values. All the methods return statements like, I have not yet been defined, that kind of thing. That's the most coarsest form. Now the whole thing exists, right? Everything's functional. It's just that it gives you the worst answers. There's no granularity. And then your next time through, you start to add some better behavior to each of these things. And you keep doing that until finally the whole thing is completed. And there's this cute picture here. Ta-da, cute picture. So in incremental, again, you're building a piece at a time. And in iterative, you're building the whole thing, but you're adding detail each time. I'm not going to spend a lot of time on these because you notice how we're starting to get repetitive with some of this stuff. Incremental, develop high risk or major functions first. If this doesn't work, nothing works. Okay, let's build it first. How can you build the most critical part first and test it? You don't have the other parts. How do you do it? Like a prototype, right? But how, for example, people need to get data, and several teams in this class are doing it. And I always have people in CS225 doing it. A couple of years ago, the student in CS225 wanted to build some software that would capture and analyze and store and print out pretty graphs for data that they were getting from a weather balloon. And it was a real live Daytona Beach campus student project weather balloon that they could throw up in the air, and it was sending all this data back all the time. And he's building his software to capture this data and do stuff with it. And what was my first piece of advice to that person? This just goes with this high risk type stuff. Because he didn't have a balloon, right? How's he going to test his software? How's he going to develop his software? Use dummy data. Simulate the balloon. Well, that's awfully easy to simulate the balloon because all it is a data stream coming in. And if you know the format of the data, you can have basically a random number generator spitting out data, garbage data in the proper format. Or you may have recorded data. Maybe they launched a balloon and they retrieved it and they had recorded data on a chip somewhere. Oh, cool. Now you've got recorded data and you can build a simulator that plays it back to you as if it was in real time. So you can do things like that. You can always build simulators. And that's kind of my, one of my pieces of advice is always, solve one problem at a time. One problem is parsing the data. How are you going to learn how to do that? Okay, pretend you have data. So everything is build your high risk first. This is risk mitigation. Notice how often risk mitigation comes up. If we can't do that, or if we fail here, the whole project gets scrapped. And you're building the operational product. That's nice because again, you get the customer feedback, or sometimes we have the term a minimally viable product, which means if we deliver this minimally viable product, we get all our money. Customer response, breakdown of tasks, again and again and again, we get to that. Notice what it says, initial product delivery is faster. Initial, that doesn't mean the total product delivery is faster, because that depends on how many times are you going to iterate, right? Risk of changing requirements is reduced. Let's parse that sentence carefully. The requirements may change, but because you haven't implemented the whole thing, the risk is reduced. Right? You're adapting to the risk you're adapting to the change. Good planning and design. Oh, okay, because think about what's happening. Again, you're doing this incremental build. You really have to plan that out properly. Early definition of a complete and functional system. Now, this is where we veer off from the agile models, which say we don't have a fully defined functional system. We've got a really good idea of the high-level architecture. By the way, you notice that's the inherent contradiction of the agile system, is we want to build these things out piecemeal, and yet you need to have some idea of the overall architecture before you can build out piecemeal. You have to have well-defined module interfaces. That you cannot get around. If you're going to build things in piecemeal form, you have to have good, well-defined interfaces. And total cost, not lower. Notice the initial delivery was quicker, but since the total cost is not lower, the total delivery is not guaranteed to be quick. I'm going to go with new technology on that one. I'm going to speed up a little bit because we're already at the hour mark. Okay, spiral model. Yes, I've seen people do spiral model before. And again, it's in form of incremental, but the people like this chart. So it's spiral model. And what you're doing is every time around the circle, you're adding functionality to the product, much like prototyping, much like the iterative development, not the incremental, but the iterative form. And what you're doing is you're breaking this thing up into these 4 phases, and that's why you're going around and around and around the loop here. And because you're adding more functionality each time, you're further away from the location. So it makes this lovely spiral that people like to say we're using the spiral model. And again, people do this with, it helps with risk mitigation because you're building it out one piece of functionality at a time. You get to modify at each phase what you think you should do next. Not always a good idea, but at least the options are there. So when you're planning the next phases, gosh, that kind of sounds like a sprint. But this I've seen again where people were worried about they're developing something new and they had some risk issues. They were a little worried about, can we deliver on time with all of the functionality? Notice right up to that we talk about risk. Users see the early development, again, rapid. It's a form of prototyping. You do your high risk stuff first. All this looks familiar, right? So I'm going to go through them. Time spent for evaluating risk too large or small for a small or low risk project. So again, if you have something that's fairly straightforward, you feel confident you know how to do it, or your team can do it, or your company has the expertise to do it, you don't use these risk mitigation techniques so much. You may fall back to waterfall if you feel really confident you're going to capture all the requirements correctly up front. Or you may go to stick with the agile forms just because that's the process you guys use. So we have, notice all the times risk shows up, risk. Spiral may continue indefinitely. Remember the other iterative forms? The iteration may continue indefinitely. That's a problem. That's a risk. Again, why is that? Software is never done. I've never had a student turn in a piece of software and say, I am done. They always say, here's my software, and what I really want to do next is add da 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 da. And I mean, even at the end of the semester, people turn in their projects and they never say, here's my project, this software is done. It's always, here's my project. And boy, I wish I could have added this or that or the other thing. And I encourage them to do that, of course. Software that's done is dead. Software always has some kind of a next level that it can go to. Again, a difference, I think, from hardware. Hardware, once you build it, bend it, bolt it, it's done. And if people want to upgrade it, they're like, well, let's go to the drawing board and start on a new thing. Right? Starting from the old thing, we'll build a new thing. Similar things, right? Creation of a prototype, cost and risk evaluation are important. Users are unsure of their needs. Notice how often that comes up. It's not because users are stupid. It's because nobody knows how things are going to affect them until they actually use it in their environment. And a resetting of the incremental versus iterative. Incremental, you don't have the whole thing out initially, you're building piece by piece. Iterative, you have the whole thing, but you're getting more and more granularity. And now we go to Agile. Now I'm not, since we talked so much about Scrum, I'm not going to talk about much here, except we're using Scrum in this class. Look at all these other forms. Adaptive software development, feature-driven, crystal clear. Crystal clear is a real intensive, hardly any documentation, lots of programming. Extreme programming is the same way. It's named extreme programming for a reason. Rapid application development. It seems to me that that is a prototyping type method, actually. It's framed in terms of sprints, but it's a prototyping method. One that's not in here, might be under feature-driven, is a test-driven software. You write a test, you fail the test. Write enough software to pass the test. Right. So we think of it as we write software and then we test it. But here you write the test and fail. And then you write just enough software to pass the test. Why are you doing that? Well, remember the rule, never do anything that's not required. Where did that test case come from? It came from a requirement specification. Oh, okay, so if it's a requirement specification, it came from a requirement. So you're literally trying to build just enough software to pass the requirements. All right, I've been yapping for a long time. Let's go back and I want to hear feedback from you guys. What is your experience in this class, in any other class? Where do you find that you've used these models? What do you see as, let's stop there. Where have you used these models? In addition to the waterfall, other models that you have used, obviously Scrum here. What else?
I think we used waterfall in 225.
Yeah, well, and what I do is I try to introduce the Agile Scrum terminology. So we do have sprints, but it's got a heavy waterfall nature because I'm asking you to do requirements up front and design up front. And then the build is really the only Agile part. And I'm hoping to introduce that terminology to get you prepped for this class, because everyone that takes 225 takes SE300. So to get the terminology there and the idea of a sprint in there and a tracking backlog, that kind of thing. Yeah, so waterfall was 225. Where else? How about in clubs? You guys develop club, even hardware. You guys in any hardware clubs the Baja Club, the Game Development Club, Rocket Club, UAV clubs, anything? Nothing? How about a prototype? I'm sure some of you guys have built prototypes somewhere before, either a physical mechanical one or a software one. Outside of CS225 in this class, Alik says not really used any formal models. Okay. I mean, even fixing stuff around the house, I might say, well, before I fix that for real, I'm going to try this kind of temporary fix and see if the idea is any good. And then if the idea is good, I'll go back and do it properly, 6 years later. Okay. How would you describe, maybe this should be a homework, part of the homework assignment for this, is these issues, how do these issues, what would you describe as the issues and how they keep coming together? What's being done here? What are these processes trying to do?
Help you make a good product.
Exactly. But what's all the dirt that comes with that statement?
Stuff like defining what a good product is.
Right. What is a good product? What is a good product? How do you know? How do you remember the bottom line? You can have it good, fast, or cheap. Pick two. That's the summary of these issues. It all plays together. There's changing requirements, misunderstood requirements, not because the customer doesn't know what they want, not because the developers know a bum, but because of the inherent nature of knowing what you want and communicating what you want. It's a very real thing to not know what you want until you experience it. How many of you guys have ever gotten a game, a video game, and you're playing the game and you really love it, and then you say, I really love it, but I wish I could, fill in the blank? Has that ever happened to anybody here? I would be shocked if it didn't happen to somebody. Well, did you know before you bought the game and played it that you really loved it, but I wish I could? Did you know that I wish I could blank was there before you experienced playing the game? I would think almost certainly no. Because the experience of using the product gave you insight into something that would, in your mind, make the product more convenient for you. And that's called normal. That's how every customer of every software product is. Now, once you play that game, now you want to buy a similar game or the upgraded version of that game, and now you're looking for it, right? I mean, it may be, depending on how important that thing was. Some of it might be like, man, this game would be so great, but this is like a fatal flaw. It's missing this one component, this one capability. So now when you go to see another game, you might actually actively look for that. And that's the way customers can be. So if you're in a hospital and you're a nurse and you're working at the nurse's station for 5 years and you see how that software has helped you and failed you, you have very clear ideas of what you're going to look for in the next software buy. You know, we used to use Blackboard here for our course management system, and now we use Canvas. And I had very clear ideas. You know, I didn't have a choice, right? The administration says you're using Canvas now. And I'm like, I hope it does this, this, and this that Blackboard does. Or I hope it doesn't make me do this, this, and this like Blackboard made me do. You know. The reason the camera was shaking was because where is he? Where are you, Farrah? I can't find him. Anyway, dog was shaking the camera, sorry. So you don't know until you experience is the bottom line with that. What else is happening? This notion of making good software. How about what we just talked about was a validation, right? What the customer wanted. Verification. Making sure that you built it right. That's also an aspect of good software, right? All these models are doing the same thing. They're trying to manage a way to figure out what the customer wants, build what the customer wants, verify that it was built, all within a time frame that is reasonable, whatever that means, and at acceptable cost, whatever that means. Acceptable cost varies widely on the customer. I don't know how much games are. I never play. But if they were like, I don't know, $1,000 to buy a game, I wouldn't buy it. If it was $10 to buy a game, oh, okay. If I had time, I'd probably look into that. So cost. Managing all these core software engineering issues. Actually, these slides should be updated to remind you of what those were. The core issues. The intrinsic hardness of understanding software comes into play. The changeability of software comes into play. The issues that what you develop is not repeatable. Not really. You build a brick, a physical brick, and you can use that brick in any building you want, right? Someone can take that brick and a good brick mason will put it in any building you want. Now take your software and try to put it in any computer you want, in any operating system you want. The same software, not a different version of that software. It's literally the same executable files. They don't transport properly like physical objects do. So this notion of deployment, all of those are tough things that are unique to software engineering. And how are we trying to handle that? Well, let's see. All of these systems are trying to do the same thing. And I tend to bring it down to change and managing change, either by constricting change or adapting to the notion that change will occur. That's what iterative stuff is doing. And or doing risk management at each cycle so that you can try to make good decisions about how to go forward in that changing environment. So that's the core of what these approaches, but all of them also share this approach of, hell, nobody understands the software. The software works and we don't know why. The software doesn't work and we don't know why, right? Nobody understands the software. And that's what also different forms come down to. software design, the waterfall model, how do they try to handle understanding the software design? How do you think the waterfall model tries to handle that problem? Nobody knows this. Nobody knows the design. Here's how we're going to try to make sure everybody understands the design. What do you think the guess? What's your guess? Documentation, absolutely. That's why waterfall tends to have a heavy documentation trail. Now, Agile Scrum, how do they handle software understanding? Again, what I'm talking about is everybody on the team has to have the same view of the software. In a waterfall model, you document the software, and then everybody on the team is supposed to read the documentation and understand it and have a shared vision. But in the Agile model, right, co-located teams with osmotic communication. So the idea is everybody has an idea of what the software is because you literally are in the same workspace. And just by nature of the fact that you're watching each other draw on the whiteboards, or you're asking each other questions, or you're saying, hey, check my work, in an informal way, you get shared vision. And I saw that happen. I was in a team meeting last week, and someone said, I can't do such and such for a valid reason. And someone else immediately said, oh, I know exactly what you're working on. I can finish that part up for you. And that's exactly the kind of team knowledge, team level knowledge that you're trying to achieve. And it's hard to do with documentation. Sometimes it's necessary. So there's not, by the way, when people say, oh, we're Agile, we don't do documentation, they're not doing Agile, right? The documentation is still there, but there's a communication aspect. Now, since the communication aspect is the way they spread the vision, you can see why there's a size issue with the Agile Scrum method. And I think earlier we were saying maybe 8 to 10 people is about as big a team as you're going to get. I worked on a team in the 80s where we were doing some research software, and we were kind of doing Scrum without knowing it because it hadn't really been invented yet, but we were only 6 people on the team, co-located, talking to each other all the time. We knew each other's pieces of the code enough to where we could feel comfortable working on them. We didn't have the formalized sprints that Agile Scrum has, but that experience of working in that co-located space was very natural. We didn't need a lot of documentation of system level, high level architecture. Quite frankly, we were all just hacking away, so we maybe didn't even have the expertise to create that kind of documentation. But notice that, again, everyone's trying to solve the same problems. What I'd like for you guys when you leave this class, I'm hoping have an appreciation for what those problems are, that you can articulate those problems to people. So that when people are, number one, when people are trying to hire you, you can articulate what the core issues are. And number two, when you're working, you have an awareness of what those core issues are. If you're being hindered by things that you don't understand, it's very difficult to find a solution. But if you're being hindered and you're saying, oh, wait, the core issue here is, we don't have a clear requirement. The core issue here is we have a different understanding of the design. Then you can start to find a solution to the problem. So that's number one. When you leave this class, have an understanding of the issues that all these different frameworks are trying to solve. And number two, have a clear understanding of at least one of these processes, of which the Agile Scrum is the one of obviously that we're working on. So if you come out of here and say, man, I really understand Agile Scrum and I really understand why it's built the way it is, then this class has served you well. If you can take that same idea and say, gosh, Agile Scrum this is why Agile Scrum is built the way it is. It's trying to solve these problems. And I understand now how to solve those problems in another way using an incremental model or a spiral model or a waterfall model. Then the course has really served you well. Because now you have options when you go out into your future projects. How are we going to do this? Oh, we should do this one, prototyping, because of da 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 da. Okay. Any final thoughts here? Is any of this coming together, or am I just rambling on? You're just trying to make me feel good. It definitely is important.
Well, like it is. So taking this, I wish I would have taken this class before I had the internship, because so much of what happened there is stuff that we're learning here. If that makes sense.
Right, right. So I know, yeah, and I know you had the internship, and I'm hoping what this class does is give you a reinforcement. Either way, it worked out, a reinforcement of what was going on in the internship, because you got to see how things worked in the internship. And now I'm hoping you're seeing maybe why things were working that way in the internship.
Yeah.
Maybe that's an optimistic thing, right? Real
Yeah.
is clearly important. Now, has anyone else Sarah had an internship with software where they were doing Agile Scrum. Has anyone else had an internship in a software, a real business software business, or a business where you were on a software team? Or I don't think you have. Tyler has. And what was your co-op, Tyler? If you don't mind.
Yeah, sure. It was in high school. I was working with Hensel Phelps Construction Company's IT department.
Okay.
It was like when I was first starting to get into computer science and seeing if I wanted to do it. Right.
And clearly it was a good experience because you're still here.
Yep, that's true. And
so
they followed. Sorry,
go ahead. I was going to say, were they developing products? And if so, what was their process?
Yeah, they were making some in-house software. I forget what it was. It was something about like employees, some kind of employee database where you could see the different roles that they had. And they used Agile Scrum. Okay. All right. And so hopefully, again, what we're doing here is reinforcing what you saw there, so you can understand more deeply what's going on and why it was built the way it is, and why any of these models are built the way they are. Yeah, it definitely is. I don't know the other person's name, but I also wish I had this class before that internship, so I knew about the process. Yeah, that other person was Sarah, by the way. Oh, okay. Yeah. All right. All right. Well, okay. Well, we always hope this is kind of one of the midpoint seminal class of a software engineering program, and I would say for all the people getting minors, for the CS minors too, because you've had 2 programming classes, and now you're having hopefully a fairly sophisticated programming class about beginning to think about construction, not just programming. All right, we've been here long enough. If there's questions, let's entertain questions, and if not, let's all get out of here. Okay, Team 12 meets right after this. I will not be in that particular team meeting. Other teams, I'll start scouring Discord again and try to meet with you as I can throughout the week. Okay. Bye all.